Welcome back. So this is so fun. I love this stuff. I was just putting together my notability notes by grabbing figures from my talks and books and stuff, and I just was marveling at the beauty of the subject that we're about to talk about. And if you're anything like me, um, prior to making this an everyday thing, stress and strain were just annoying. And the reason is because I just could never tell the difference. I didn't, like, I don't know. For some reason, I couldn't connect in some way to understanding what they were. And so, what I want to do here. This is because we're talking about active matter. We're talking about field theories. We're talking about deformation and flows in biological materials. And the natural language for this is continuum mechanics. It's the field theory of materials. And within continuum theory, we need to talk about the geometry of our material bodies, and we need to talk about the forces that act on them. Underneath it all, what we have is F equals ma. We're not thinking about relativity or anything like that, and so we're talking about classical physics. And in classical physics, Newton figured it out. And Euler, among others, saw how to generalize it to continuous media. So what did Newton figure out? He figured out that force and acceleration are linearly related to each other, and the proportionality constant is the inertial mass, if you will. And I don't need or want to get all technical about that, but it's just to say, that this F equals ma thing is got so much reach. You can really, really pull off a lot of stuff by knowing that. So at any rate, when we turn to continuous bodies, we have to talk about the force and we have to talk about the geometry. So let me note that. So this is force per unit area, and of course I'm going to go into this in some detail. And this is dimensionless measure of relative displacement. Okay, that's super important, this relative point. In other words, if I take my my iPad, which you can see right here, and I move it, that's not a deformation. Or at least it's not an interesting one. There's no relative displacement of the material particles inside of the iPad, and so it's not deformed. Strain measures, like I take my glasses and I bend this thing. That is strain because I'm making relative displacements of the material particles. Okay, enough about all that. So let's talk, for starters, about material response. So, this is a biology course, or at least it's a biology-oriented physics course, or it's a physics-oriented biology course or something. I don't know. It doesn't matter. What we're trying to do here is we're trying to understand the great mysteries of the living world, and the point of view of this particular course, of my research career, is that by no means is going at it from a physics point of view the only way to go after studying living matter. That's so obvious that that's false. It's because of the huge achievements that have been made in the absence of sort of a physicsy approach. I'm just saying it's an approach, and so we're trying to physics the living world, and at the moment we're thinking about the nature of active matter and so on. And this schematic of an experiment is really, really cool. And you know this from your own experience. If you, at least in my age group, you played with silly putty as a kid. And silly putty, if you took it and you threw it at a wall, it bounced off like a perfect rubber elastic ball. And if you left it on the floor, it would end up no longer being spherical. It would deform. So it had the properties of both elasticity and viscosity. And so the idea here is that I have a cell between two plates. We put a weight on that, and we wait a certain amount of time. If the certain amount of time is short, then when we release the plate, as you should see in the upper right, it will bounce back to its original shape. And if you kept the load on for a long time, then when you remove the weight, it doesn't change its shape back to the original shape. That's because it's been permanently deformed, and that's known as viscous deformation. And really, what we're going to be interested in doing is learning how to think about elastic materials, learning how to think about viscous materials, learning how to think about what happens when something is simultaneously elastic and viscous. And once we've done all that legwork, then we'll finally be prepared to then add on to that mix activity And what I mean by that is that the stresses are generated from within by virtue, for example, of the cross-linking of microtubules by motors, just to name one example. So anyway, this is just to lay down some language about what I mean by elasticity. And, I'll actually comment on this now by saying that here, stress and strain are linearly related to each other. And for the viscous case, what I'm going to say is that stress is proportional to d by dt. I'm being sloppy here, so don't take it too seriously. But this is the strain rate. So that's what we're going to end up concluding about viscous materials, is that the stress, the force, is related to the rate at which you deform them. Think about that. Think about silly putty. If I had a piece of silly putty and I throw it against this wall right in front of me, it's going to bounce back at me like a tennis ball. The reason for that is because the strain rate is very high. The rate at which, just like, if you look at a high-speed photography image of a baseball bat hitting a baseball, or Tiger Woods golf club hitting a golf ball, I'm not into golf. I don't have any attachment to that, but I sure as heck like looking at high-speed photography of a proficient golfer hitting a golf ball, because the amount of deformation is huge. The golf ball gets monstrously deformed, but it happens very fast. And so at high strain rate like that, you get an elastic response. But if you take that piece of silly putty and you push on it really slowly, but with the same absolute force, it will deform differently. So that's all I'm trying to say, is that there's some interest there to those different kinds of scenarios. So in my last vignette, I already introduced the experiments of Robert Hooke, and what I want to do is I want to focus on this particular experiment. So this is the simplest, in a way, the simplest experiment. And what I would say about this one is that what Hooke did is he says, well, I'm going to look at the force acting downward divided by the cross-sectional area, and that is going to be equal to a modulus, which we're going to refer to as the Young's modulus, and then times the strain. So I'm going to unpack all this. You don't need to get too worried about it at the moment. So this is the stress, and as I already said, that's the force per area. That's measured in newtons per meter squared, which is the same thing as pascals. And then this thing is the strain. Note what the strain tells us. It's unitless, first of all. It's important to notice that. And it tells you about the fractional change in length. And then finally, this guy is the Young modulus, named after Thomas Young. And the Young modulus has units of newtons per meter squared or joules per meter cubed. And this is just to remind you of what I said yesterday, that we can think about elasticity using either a force mindset or an energy mindset. Both of those worldviews are useful, and I'm going to pass back and forth freely between them. And so when I say something has a megapascal or gigapascals for its Young modulus, you could think of that as newtons per meter squared. In other words, it's the stiffness. So the Young's modulus is a measure of the stiffness. It tells you how happy the material is to deform, how much deformation you'll get for a given amount of force per unit area. So if the Young's modulus is very large, notice, I can rearrange this. I can rewrite this as, if I want to find out what the displacement is, I can rewrite it as strain is equal to sigma divided by E. So this is strain. Oh boy. That's really a pain. Sorry, this has happened a few times. I just ask your patience. Don't know why I get kicked off now and then. So anyway, that's the strain, and then this is the stress. And what I'm saying is, I apply a given stress, And then how much strain I get out of it is going to be inversely proportional to the Young modulus. If the Young's modulus is large, then I don't get much strain for a given amount of stress. And if the Young's modulus is small, which means the material is soft, then I will get more bang for my buck, so to speak. Okay, so what have we what have we accomplished thus far? So that was a first. Let me call that a first qualitative introduction, or maybe I should better say semi-quantitative, or I could also say one-dimensional, which is really that's really my hang-up. It's actually quantitative. It's just first qualitative, semi-quantitative, or one-dimensional intro to stress and strain. And the reason I'm waffling a little and not saying, yeah, we're done, we talked about stress and strain, is because the way we deform materials is more complicated than just changing their length. So like if you look at this cube, I can deform it in the way that I show you here. Like imagine a cubic piece of Jello. Like I always think of Jello as like the funnest way to imagine stress and strain. So I have my piece of Jello, and then I grab the faces and I pull, and then I might twist a little, and when I do so, I'll get some complicated shape. And the way I described stress and strain earlier here is not general enough. In other words, I pretended, if you like, that stress and strain are scalars. That's another way to say about the incompleteness of the formulation that I just gave you. And this is the earliest formulation of people like Hooke. But along came Euler, along came Cauchy, and they realized that, well, we should think about more general states of deformation. And so, that led to, I showed you this in the previous vignette, but it led to the articulation of different kinds of field variables. So at the top, we've already talked in detail about the concentration field, which is a scalar field. We will be talking now about displacement and velocity, but we've already talked about flux, which is a vector. So flux tells me the number of molecules crossing unit area per unit time, but in a given direction. So, in other words, it's got x, y, and z components if you want to use Cartesian coordinates. And now we're going even more general to what's called a tensor field. And, the way I want you to think of this is the way I suppose that you might want to give an intuition is that at every point in space, you need a 3x3 matrix. Again, I'm being incomplete because it's actually more general than what I'm saying right now. But for our purposes, for the moment, I want you to think, okay, well, at every point in the space, in my piece of aluminum or inside of a cell or in the blob of birds, whichever, or the sea lion impinging upon a school of fish, in all of those cases, at every point in space, I have a matrix, and that matrix describes for me the current geometry in the form of what's called a strain tensor. And I'm going to try to, today I'm just giving a rough impression of it, as we do elasticity and fluid mechanics and viscoelasticity and then finally active matter, we will over and over again see this. And let me, Herodotus said to be forewarned is to be forearmed. I'm going to give you a homework problem, which is literally nothing more than being like Steph Curry, who's an NBA basketball player, and doing your 1,000 free throws per day. I'm giving you an exercise on what's called Einstein's summation convention and indicial notation, and it is for no reason other than to practice, so that when you watch what I do in class or in my vignettes, you'll be more fluent in the notation that I'm going to use, because it's a huge labor-saving device, but actually it's even a conceptual device. When you write Maxwell's equations in Cartesian coordinates, they're ugly and they're not very easy to understand. If you write them in vector notation, meaning divergence of E and divergence of B and so on, there's a concept that goes with that. When I write the divergence of E, for me, I think, oh, that means I'm doing an integral over a surface of a flux, just for example. And so the bottom line is that writing things down in terms of these these tensors is very powerful for us to think about the nature of the deformations that are going on in a material. So what do I want to say? I guess maybe I will just give a first introduction to a few pieces of this. So let me broaden this. So first, I want to give an introduction to indicial notation, which we will use very frequently. So I can write the vector A as ax, ay, and az. Those are the Cartesian components. You might be used to that. And I'm going to start writing that as a1, a2, and a3. And the reason for that is that by virtue of using numbers instead of letters, I permit myself then, for example, to be able to write things like the dot product, which you'll remember is equal to ax bx plus ay by plus az bz. That's also equal to, in our new notation, a1 b1 plus a2 b2 plus a3 b3. Notice how it rolls off the tongue faster? And I can rewrite that as sum over I equals 1 to 3 of ai bi. Now we're getting somewhere. And finally, I can write that as ai bi, and this is the so-called Einstein summation convention. And what does the Einstein summation convention say? It says sum over repeated indices. So that's the idea. So sum over repeated indices, and let's look at an example. So you might remember that the divergence of a vector u is given by dux by dx plus duy by dy plus duz by dz. You might remember that. And we will rewrite that in our indicial notation like this. Okay, so this is already much more convenient, du3 by dx3. And then I can write that as sum I equals 1 to 3 of dui by dxi. And finally, I can write that as dui by dxi. This is with Einstein's summation convention in effect. So what I'm telling you is that, very interesting and useful, I'm telling you that this thing and this thing are equal to each other. They're the same thing. And honestly, those are kind of the only two that I would normally use in my own notes to myself when I'm doing calculations. I'd either write it in direct notation, which is what you see the pink box in the upper left, or I'd probably write it in summation convention, as you see in the lower right. Let's tackle a little. I'll give you one more example, just in the name of trying to prepare you for things that you'll do in the homework. And I want to introduce a symbol, epsilon ijk. This is sometimes called the Levi-Civita symbol. And epsilon ijk is equal to 1 for 1, 2, 3, or 3, 1, 2, or 2, 3, 1. It's equal to minus 1 for 1, 3, 2, and then 1. Oh, I already did that one, and then let's see which one comes next. 3, 2, 1, and then 2, 1, 3. So, and it's equal to 0 otherwise. So you might be saying, well, what on earth what purpose does that serve? So this Levi-Civita symbol, so these guys, just so you can note this, they're the cyclic permutations of 1, 2, 3. And then the next group, there's an anti-symmetry. In other words, I've mixed up the order, a 1, 2, 3. Notice that in the top group, I'm going around a circle. 3, 3, 1, 2 is the same as 1, 2, 3 because I'm going around in the circle. I could write this as a triangle. You know, like you could, if you wanted, you could think of this as 3 vertices, 1, 2, 3, and you're going to travel around clockwise starting at any vertex you want. So if I start at the bottom left, I have 1, 2, 3. If I start at the top left or top, I go 2, 3, 1. And if I start at the bottom right, I get 3, 1, 2, going clockwise. And the other ones are the ones that I get from going counterclockwise. That's another way to think about it. Okay, so what purpose does this serve? Well, let's take a look at A cross B. If I want to know the ith component of A cross B, my claim to you is that this is equal to ijk, aj, bk. Let's try that out. So the one component of A cross B, according to this, is equal to epsilon 1 j, k, a, j, b, k. Now, this says sum over j and sum over k. They're both repeated indices. So, okay, I'm going to be pedantic about it. So epsilon 1, and I'm going to do the j's first. So I have 1, 1, k, a, 1, b, k, plus epsilon 1, 2, k, a, 2, b, k, plus epsilon 1, 3, k, a, 3, b, k. So I've done the j sum. Now I have to do the painful k sum. So that's going to give me epsilon 1, 1, 1, a1, b1, plus epsilon 1, 1, 2, a1, b2, plus epsilon 1, 1, 3, a1, b3, and so that's this first guy. Then I have plus epsilon 1, 2, 1, a2, b1, plus epsilon 1, 2, 2, a2, b2, plus epsilon 1, 2, 3, aha, that one looks good, a2, b3. And then I'm going to go on to the final one, which is epsilon 1, 3, 1, a3, b1, plus epsilon 1, 3, 2, that one's a good one, a3, b2, plus epsilon 1, 3, 3, a3, b3. Okay, by the definition of the Kronecker delta, sorry, the Levi-Civita symbol, this one is 0, 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 this one is 0. All of those are 0. So what I'm left with when all the dust settles is a2, b3 minus a3, b2. And that's exactly what you would expect from the vector cross product. Now, again, you might be saying, come on, man, that's just gratuitous. But what you're going to see is that it actually isn't gratuitous. In other words, this is going to be a huge labor-saving device on terribly hard calculations where if you tried to do them in sort of the usual XYZ way, you would get yourself lost in a fog of confusion. Whereas if you really carry out your mechanics correctly on this summation convention stuff, you can really get some mileage. Okay, so having defined all these things for you, I'm ready to now tell you what the stress is and a little bit about what the strain is. Okay, so just a few last thoughts before we finish. So first of all, let's talk about strain. This is the general definition. And this is for, and I'm going to say for small displacements. So epsilon ij is equal to 1/2, and then dui by dxj plus duj by dxi. So that's the definition of the strain, but I need to tell you what u is. U vector, the vector u, is the displacement vector. And to see what that is, we need to appeal to this diagram. So what does this diagram tell us? So this initial, so another way to think of this is the initial configuration of my potato. So I start out, here's the container for my, my headphones, and I start out, this thing is undeformed. And now I'm going to squeeze on it. You can hear it. Here, I'm squeezing on this thing. And when I squeeze on it, the reference configuration is replaced by the deformed configuration. There's a new set of positions for every material point inside of this object. Here's a water bottle. So I squeeze it, you know? And when I squeeze it, you can see from the side view, it's deformed. You know, with this camera, it's really weird, but I'm squeezing on it, I hear it, and I'm deforming it. So the bottom line is that there's a new position for every point. So the way that I've defined this is that capital X is the original reference position of a given material point in my continuum potato. Then I do my deformation, and every material point moves to a new point, which I'm going to label as x, little x, of big X and t. In other words, it's a function of where you started, which is capital X, and of time. And I can rewrite that as the original guy. So another recasting of this is that x of capital X and t is equal to original x plus u of big X and t. This thing is the displacement. So it's a rule. You know, think of Manhattan, if you like. If I start out, you know, I've got a grid, and I'm at some point, some intersection of two streets, one north-south and one east-west, and then I have a displacement. I go to a new position, and that vector u tells me how to get to my new position given my starting position. So the strain tensor, look what it does. It measures the displacement gradient. It tells you how the displacement changes in space. All right, let's look at an example here. So the example I'm giving you here is that I have this original object, which is a square, and my rule is very simple and shown right here. The rule is the farther you are from the y-axis, the more you move to the right. That's all that rule says. You can see that with these red vectors. So what it's saying is I want a displacement. The displacement is only in the x direction. You can see that because u2 is equal to 0. I displace in the x direction proportionally to how far I am from the y-axis. And what that gives me, according to that, I can just do it. So epsilon 1,1 is du1 by dx1, and that's equal to alpha. Epsilon 2,2 is equal to du2 by dx2. That's equal to 0. There is no u2, and so that thing's 0. And then, you know, epsilon 1,2 is du1 by dx2 plus du2 by dx1 times 1/2, and that's equal to 0 as well. So that explains why the strain tensor takes that particular form. The next one is more fun, or a little bit more complicated, because here, this one, we're doing an areal expansion. This is saying move in the y direction proportional to how far you are from the x-axis, move in the x direction how far you are from the y-axis, and that basically causes this thing to swell. And the square goes into this configuration, and the strain tensor is, in 2 dimensions, is this diagonal alpha, alpha, 0, 0 thing. And then finally, this last one is the most amusing of all, because here it's saying that displacement in the x direction is proportional to how far up you are from the x-axis. This is called a shear. You can see it with these red arrows. The farther up you go from the x-axis, the more you move in the x direction, and so that leads to turning a square into this shape that you see here. And now the strain tensor is this off-diagonal functional form that you see in the lower right. So this is my introduction to strain. What's the summary? The summary is 2 things. 1, strain is a geometric, dimensionless quantity that tells us about relative displacements. If I move my water bottle from here to here, I do not strain it, because there's no change in relative position. It's absolutely mandatory that you keep that in mind. It's relative displacement, which is why we're computing the gradient in the displacement vector. The second thing is that it's tensorial, and we worked out some examples. And for fluids, what we're going to find is that we want to think about the so-called rate of deformation tensor. Note at the top here, this d is the rate of change of velocity. So this thing has units of 1 over t because it's the gradient of velocity in position. So the units of that thing are 1 over time, so it's the rate of deformation tensor, or the strain rate is another thing that people call it. Now, so I've told you about strain. So now what I want to do is just say a few words about stress, and we'll come back to this in earnest later. But the stress is this very subtle and cool idea that if I have a continuous material body, the force on a little cube of material is going to come from all the faces. Like, again, think of your piece of Jell-O. You can grab on the top of a piece of Jell-O and you can slide it, you can push down, and you can twist it. In other words, you can push it in the X direction, the Y direction, or the Z direction. And that's on just that face. And if I have 9 faces on my cube, I can do a vector on each and every one of those faces. And this strain tensor is what tells us about the force on the planes on this little material cube. The units are force per unit area, and when I talk about force balance later, we'll have an opportunity to look at this in some detail. I think for now, I'm going to leave it to just saying that, we've kind of talked about what the idea is. So here's where we are. We're going to invoke our continuum protocol after I do one sort of last vignette, which is still a bit in the scratch and sniff variety. I'm going to talk to you about elastic deformation of beams. And once we've done that, then I'll have a bit to say about a more general deriving field equations in all of their tensorial glory for solids and fluids and viscoelastic materials, again, in preparation for thinking about active biological materials. So I think for now that's the key elements of what I wanted to get across.